So Nick is going to continue with some more examples of harmonic mass forms. Over to you.
Thank you. Can you hear me? It sounds like it's on. So today we're going to do some more examples of harmonic Maass forms. Primarily, I'm going to work in more of a sort of arbitrary weight situation, maybe with an eye toward half integral weight at the end. I want to remind you of this multiplier system that we used last time. It's going to come up again. And I wanted to remind you that, remember, this is almost a homomorphism, but there's this extra factor here that, at least in half integral weight, could be plus or minus 1. So that will come back in just a minute. So the goal, the first thing I want to do is actually construct harmonic Maass forms for a given multiplier system and weight and group. And the way to do that is by averaging. So what we're going to do is, this is called the Poincare series. And what we do is we'll start with some function phi, and I'm not going to make really any assumptions about this yet, except that it's translation invariant. And depending on your multiplier system, you may actually not want, you may not want phi to be translation invariant. You may want to get out some root of unity or something, which shows up sometimes with different multiplier systems. But for right now, let's just keep it simple. So we're going to start with a phi that's translation invariant. And what we're going to do is sum over all the elements of our group. Remember, this gamma could be gamma 0n or something. We'll sum over all the elements of our group modulo the subgroup generated by the translations. So here, let me just put this down here. Gamma infinity is going to be the group. What's that? Is there a question? Okay. It's going to be the subgroup of all the translations. Okay, and if we mod out by gamma infinity, then what we can do is we can take our phi and then slash it in weight k with gamma, and then I'm also going to multiply by the conjugate of the multiplier system. Okay, and we'll call this thing p phi tau. So I guess I need to put a tau somewhere. Okay, and this is a well-defined sum because phi is translation invariant, so it doesn't matter which coset or coset representative we pick, mod gamma infinity. Okay, so I claim that P, that this Poincare series is, or at least is modular for the group. So let's do this. So really briefly, I want to just say one consequence of this relation here, and you can check this. This isn't too hard, but what it basically is saying is that if we slash, we take a function and slash twice with two different matrices, well, we should expect that it's the same thing as slashing with the product of the two matrices, except that it's not quite that because of this multiplier system. And what you end up getting is, oh, I did this on the side that I didn't want to. Maybe I'll put the equal sign here, and yeah, I wanted to put the omega here, gamma 1, gamma 2. And so we'll need that. So let's show that P transforms correctly. So if I take some gamma 2 in gamma, then P hit with gamma 2, this is the sum overall, let's say gamma 1s in gamma mod gamma infinity. of nu of gamma 1 bar phi slash k gamma 1 slash k gamma 2. Okay. Now I'm realizing I do actually need to make some assumptions about phi. For example, I want to be able to actually do this sum and make things make sense. And in a minute, I'm going to rearrange the sum. So it seems like maybe we want to assume that the sum converges absolutely. So we do need to make some assumptions about phi. So we'll assume that the sum converges absolutely. And there are some estimates that we could do to say how big phi needs to be. That's not so important right now. Let's just assume that phi decays well enough that this converges absolutely. And when we start plugging in actual explicit things for phi, then we can talk about that. Okay, so what happens here? Well, this piece right here is going to give us omega gamma 1 gamma 2 phi slash k gamma 1 gamma 2. Okay, and then, well, let's look at this. Omega gamma 1 gamma 2, and then I have this new bar gamma 1. Let's stare at that for a minute. That looks like if I move these to the other side, I should get something that kind of looks like this. So sum gamma 1 in gamma mod gamma infinity. Let's see, I get a new bar of gamma 2. I get, and then I guess I get a new of gamma 1 gamma 2 bar. P slash k gamma 1 gamma 2. I feel like one of those bars shouldn't be a bar. Did I mess that up? Yeah, I think this one is not supposed to be a bar. Let's check that. Oh, yeah, because this is actually omega bar. So everything that I wrote was exactly off by the bars were in exactly the wrong place. And now I think it's correct. Okay. Great. So now I'm going to make the change of variable. Gamma 1 goes to, let's say, gamma 1, gamma 2 inverse. And now I should get sum over, I'm still summing over all the same elements of the group, just in a different order. And the nu of gamma 2 can come out. And then this gamma 1, gamma 2 turns into just gamma 1. So nu bar of gamma 1, and then phi slash k gamma 1. But that's exactly p. So this is nu of gamma 2 times p. Okay, so we actually created a thing that transforms correctly under the group with the correct multiplier system, and everything is nice. Okay, that makes sense? All right, so yeah, I guess I can write down, we might as well write this down. So a good enough assumption that the sum converges absolutely is that phi of tau is less than v to the 2 minus k plus epsilon as v goes to 0. And if you assume that, then you'll get absolute convergence. So now, okay, we've taken care of the transformation law, but now if we want to make a harmonic Maass form, we want to impose the condition that it's annihilated by the Laplacian. So to get delta k of p to be 0, we need to choose p appropriately. Okay, so we're not going to exactly choose phi yet, but I will simplify it a little bit. So let's make the assumption. Where is that? Yeah. So let's assume that phi of tau is of the form, let's call it like other phi sub m of v, e of m u, and we'll say m is some integer. All of the examples I want to do today have that form, and so we might as well make that simplifying assumption. Sort of separates the two variables. Okay, so let's compute the Fourier expansion of P. So to compute the Fourier expansion of P, I know that P is going to have some Fourier expansion because it transforms in the right way. So I know that P tau is going to look something like some n in z of, let's call it B sub nv e of nu. Okay, for some coefficients B, where we can write down a formula for B of nv. This is a Fourier expansion, so we should be taking Fourier transforms. So the integral from 0 to 1 of B of phi tau e of minus nu du. Yeah, good. Okay, so let's actually start computing this. So again, I'm going to sort of ignore all sort of questions of convergence and analytic type things. I'm going to switch sums and integrals without thinking about it, and probably never say anything about it again. So I'm sorry if that's something you really wanted to see today. Well, let's see. I think once we impose this, then it's a fair assumption to say that it might have a term like this. But is everything of that form? I don't know. I don't think that's clear. I don't think that's obvious at this point. What's that? Oh yeah, good point. It's just right. Yeah, good. Okay, so let's write down the definition of P and then swap the sum and the integral. So let's take the sum out. Let's see, I don't need the multiplier system in the integral. And then, right, so then we want to do integral from 0 to 1 of P of phi. Well, I mean, let's actually like write down what the slash operator does. Let's just do it. So this is like c tau plus d to the minus k, e of b a tau plus b over c tau plus d, e of minus nu du. Okay, and now what we're going to do is we're going to think about what these cosets look like, and for this, I'm going to now assume that we're working with gamma 0 n. For simplicity, we can do this for other groups, but this will make things much nicer. So what we're going to do is decompose this e of oh, we expanded. Yeah, you're right. Thank you. That's phi of, yes. That was silly. Thank you. Okay, so it's not too hard to show that every coset is either of the form C equals 0, so something with a lower left-hand corner that's 0, or something that's, well, if C is not 0, we can take C to be positive because we're modding out by plus or minus all of the translations. And so what we'll do is we'll get a C equals 0 contribution. And then C bigger than 0 contribution. And let's write down what those look like. So when C is equal to 0, there's only one coset, and it's the identity coset. And so we'll take gamma to be the identity. And when we do that, we just get the integral from 0 to 1 of b of tau e of minus nu du. Okay? So that's the contribution from the identity coset. And then when C is positive, so we'll sum over all of the positive C's. Well, we need to assume that n divides C because we're in gamma 0 n. And now we have to think about what we can do with our matrix. Well, I've chosen C. Now I can choose D. But I need to make sure that D and C are co-prime, because otherwise I don't have a matrix in SL2Z. And now I claim that we're actually done. We now have identified a matrix. We've identified one of these cosets. And it's not too hard to show that if you take a bottom row C comma D and you lift to any A, B, C, D, just choose any matrix that you want in SL2Z, that up to gamma infinity, you've identified the only possibility. Because you can just look at what gamma infinity does to such a matrix, and it just only affects the top row, sort of modulo the bottom row. And so what we're essentially doing is just choosing the bottom row of our matrix and just saying the top row is just whatever we want, any lift to SL2Z. And so we'll just write down all of this. So this is nu bar of A, B, C, D, integral from 0 to 1 of C tau plus D to the minus K, phi of A tau plus B over C tau plus D. E of minus nu du. Okay, and now it's going to be convenient to think of phi in this way, this decomposition here. So let's look at what happens in the first bit. So in the first bit, this integral only depends on u, notice. So this is going to be phi m of v, integral from 0 to 1 of e of m minus n u du. Okay, plus some other things. I guess maybe I don't want this line here because I'm actually going to have some long equations. Okay, and then we're going to do the same thing for the C's, and I'm just going to put these together in the same sum. I'll just put everything here. So this is nu bar of A, B, C, D. And then, well, I actually want to deal with this in a second. So let's just hold off on this one for a minute. Why don't we evaluate this and just sort of deal with that so we don't have to think about it anymore? Well, these exponential factors are orthogonal. And so this integral is only 1 if m equals n, and otherwise it's 0. So this is exactly just delta mn. So it's 1 if m equals n and 0 otherwise. Okay, well, okay, so that wasn't so bad. So now what are we going to do here? Well, now we can do something kind of clever. Well, I think it's clever, and I'm allowed to say that because I didn't come up with it. So here's what we're going to do. And let's put it maybe here. We're going to write a tau plus b over c tau plus d as a over c minus 1 over c times c tau plus d. Now, is it obvious that happens? That's correct? No, it's not obvious at all. But you just sort of do the algebra, and you remember that 1 is also the same thing as AD minus BC. It's the determinant of the matrix. And you can just sort of smash this and get this. But this is very clever. So we're going to use this decomposition. And let's go one step further, and let's notice that 1 over c tau plus d is the same thing as c tau bar plus d over absolute value of c tau plus d squared. And this is the same thing as cu plus d over absolute value of c tau plus d squared minus I, let's see, cv over absolute value of c tau plus d squared. If I didn't mess that up, which I probably did. Okay, so now we can plug some things in. So we're going to take the integral from 0 to 1 of c tau plus d to the minus k. Phi is now this form, this little phi sub m of v. So this is phi sub m. Remember, v is the imaginary part. So the imaginary part is the imaginary part doesn't have the a over c in it. It's going to be the imaginary part of this. There's a minus sign there, there's a minus sign there, and there's a c in the denominator and a c in the numerator. So this is really just v over absolute value of c tau plus d squared. And then, well, I'm already out of room. There's an e, and now I need the u is the real part, right? So this u is the real part. So we need to look at the real part of this. So the real part is going to have an ma over c. cv. There's a c here, but then there's also a c down here that I canceled. Yeah, so ma over c. And then let's see, it's going to be minus m cu plus d over c absolute value of c tau plus d squared. And then, and then I even have more things because I still have e of minus nu du. So this is sort of a mess, but we're getting somewhere. So that's good. Yeah, that looks like my notes. So at least I've made the same number of mistakes as I did in my notes. And okay, so what are we going to do with this? Well, I want to make a change of variable. U goes to, let's say U goes to U minus d over c. It's going to take all of these c tau plus d's, and it's going to basically get rid of this d part, right? It's going to cancel basically all of those d's. But it's also going to shift this integral off by d over c. And now what we're going to do is choose a set of representatives, d mod c. So just take your favorite set of representatives of d mod c, and then we'll observe that if we replace d by d plus c, what it does is it's just going to take these integrals, which all have length 1, and it's just going to stitch them together. The endpoints are going to all just exactly line up. So this stitches the integrals together. And I hope that sort of made sense. Feel free to ask questions. But what we're going to end up getting, so let's take this down here. So I still have this delta mn bm of v. And then I'll have sum over c's that are divisible by n. And I'm going to have a sum over d's mod c. And I'm going to put a little x here to indicate that I'm only allowed to take the d's that are coprime to c, so the units. And then we have nu bar of a, b, c, d. And now I'm going to do a couple of things. We sort of are going to do a couple of steps at once. Okay, so, well, I have this e of ma over c, which can come out. Okay, but also I made this change of variable u goes to u minus d over c, which in every place there's a c tau plus d is nice, except right here there isn't a c tau plus d. And so this is going to kick out another factor, and it's going to be exactly nd. Okay, And then we stitched a bunch of integrals together. So what we're going to get is the integral from minus infinity to infinity. And well, one more thing is that this c tau plus d is now going to just be c tau because of our change of variable. And so now the c can actually be factored out. And well, maybe I'll put that out here, 1 over c to the k. And so now I think what we're left with is tau to the minus k, phi sub m of v over c squared absolute value of tau squared. And then we'll have e of minus mu over absolute, let's see, c squared absolute value of tau squared, and then minus nu du. I'm certain I made a mistake on that. Let's see. Does it at least match my notes? It at least matches my notes. So, okay, maybe it's okay. And so now we've sort of split this into two pieces. One piece which I think is interesting and one piece which I think is not so interesting. This piece right here is really interesting. This is a thing called a Kloosterman sum. We're going to talk about that in a minute. But this is an object called a Kloosterman sum, and those I find really fascinating. There's a lot of really interesting number theory in those. And this piece I find less interesting because this is just going to be some kind of special function. Once we specialize what phi m is, this is just going to turn into some special function, which it just is what it is, and you can look up properties of things and whatnot, but I don't find that to be so interesting. So I don't really want to focus on that part too much, but I do want to focus on the Kloosterman sums a bit. So let me write down the definition of the Kloosterman sum. Okay, so S M N C nu is this Kloosterman sum. It's the sum of D's mod C that are coprime to C, nu bar of A, B, C, D. And remember, this A and B are chosen however you want, just so that A, B, and C, A, B, C, D is a matrix in SL2Z. And then E of M A plus N D over C. And this is called a Kloosterman sum. The original Kloosterman sum, the ordinary one, didn't have any multiplier system. This is just the identity. And so it's just this exponential sum. And even those are really quite interesting and mysterious. But if you start playing with some other multiplier systems, there's also like a very rich theory here. And we'll just sort of touch on it very, very briefly. Oh, well, not necessarily. In integer weight, it's a character mod n. But in half integer weight, it's maybe quite a bit more interesting. Maybe it's the multiplier system for the Dedekind eta function, which involves Dedekind sums and sort of lots of sort of complicated things. So you're right. In integer weight, the only thing that this can really be is a Dirichlet character. So not too exotic. Are there any questions at this point? This is a good place to pause. This sum, does it depend on what A and B are? No. So it's not too hard to show that if you choose A and B differently, then you'll end up getting some factor out of this nu and some factor out of this E, and they'll exactly cancel just by the properties of multiplier systems. So yeah, it does not depend on the choice you make for A and B. Okay. So now I think it's time to talk about some special cases. So here are some examples. So what if we set phi sub m of v to be e to the minus 2 pi mv? Okay, what's that going to do? Well, this phi sub m, remember, is multiplied by this exponential factor. And so this is the same thing as saying big phi is just q to the m. And remember, I'm assuming m is an integer, but not necessarily positive or negative. And so this will give us sort of two families, depending on if m is positive or negative. So yeah, let me write that down. So phi sub m of tau is then q to the m. And I'll give these a special name. I'll call them PKM of tau, and this is going to be our Poincare series with this phi sub m tau plugged in. So now, because this seed function is holomorphic, we're going to end up with a holomorphic function at the end. And so these PKMs, these should be weakly holomorphic modular forms. And they are. So let me tell you a little bit about this. So when m is negative, well, the integral over there, which I said is just going to give you some special function, it turns out that it gives you values of the I-Bessel function. And there are exact formulas for this, but I didn't want to spend a lot of time writing down a bunch of formulas, so you can look them up. But you'll get values of the I-Bessel function. The I-Bessel function grows exponentially, and so the numbers that you get out of the integral that give you these coefficients, they're going to be very large, and so you expect these coefficients to be very large, and that's actually exactly what happens because these Poincare series are giving you weakly holomorphic modular forms and not cusp forms. So PKM is an element of MK shriek gamma 0n nu. Okay, so these are giving you the weakly holomorphic modular forms. And they're going to look like q to the minus m plus stuff. I can even do better than that. It's going to be q to the minus m plus big O of 1. Okay? What if m is positive? These are also quite interesting. So if m is positive, then the integral gives you the J-Bessel function. And the J-Bessel function is oscillatory and decays. And so these coefficients are actually quite small, which is what you would expect out of cusp forms. So in this case, PKM is a cusp form, gamma 0n. And not only that, well, okay, so there's a couple of things to say about this. One of them is that it's not actually clear at all from anything that we've done if we haven't just written down the zero function. It's like not clear if this is even non-zero. It's clear in this case because there's this q to the minus m term that can't possibly go away. But these cusp forms, it's actually not clear if they're zero. It's actually an open question to determine if a Poincare series is identically zero. Oh, yes. Yeah. So I'm thinking of this as a negative number, but m is already negative. So yes, exactly. Yeah. It's an open question to determine if these are generally non-zero. And it's expected that unless the space happens to just be the zero space, in which case, of course, they're all zero, that generically, none of these should be zero. And there are some partial results, but this is a wide open question. And it's actually, in the case of k equals 12, this is equivalent, the Poincare series non-vanishing is equivalent to Lamar's conjecture on the Ramanujan tau function. So this is hard. This is a hard question. Okay, some things we can say, however, is that if we take the inner product of an f, and let's say f is, say, another cusp form. If we take the inner product of f with PKM, and this is a fun calculation that I suggest you do at some point, you'll get gamma k minus 1 over 4 pi m to the k minus 1 times the mth coefficient of f. Yes? Yeah. Is there any good reason for these to not be zero? Oh, no, there's no good reason to think that they should be zero. But you just can't, I mean, you're writing down this thing. You can't actually, I mean, you can compute you can do numerical computations, but because of the oscillatory nature of the Bessel function, it's very hard or impossible in some cases to compute these to any sort of to enough precision. And you can in some basic cases compute to enough precision, but you can't say generally that that any of these are just not the zero function. Yeah. If pkm is 0, when k is 12, if pkm is, and n is 1, if pkm is the zero function, then Lamer's conjecture is false. Okay. Yeah, it would give you a counterexample to Lamer's conjecture. Yeah. So it's almost certainly not 0, because we believe Lamer's conjecture. Okay, but anyway, the nice thing about this formula is that this implies that the set pkm, let's say m bigger than 0, this spans sk. So, okay, that's not super helpful, to be honest, because this is a finite dimensional vector space, and this is infinitely many things. So, great, I have an infinite spanning set for a finite dimensional space. Maybe not the most helpful piece of information, but we'll see actually in a minute that actually is relevant and interesting. So here's the problem with that. In the m equal, in the negative m case, this q to the m sort of doesn't interact with the rest of the sum. But when m is positive, this sort of, there's a whole sum here, and this q to the m actually could cancel with another q to the m business. So it's actually not even clear if the q to the m term in the sum is even 0 or not from the general Poincare series. Yeah. So we don't even know if how many of these you would need, because we don't know if they're 0 or not. Okay, so let's make some harmonic Maass forms. So in the second case, let's take B to be a little bit more complicated, and this will just come out of the differential equation that you get for the hyperbolic Laplacian, and it turns out that the right thing is 1 minus gamma of 1 minus k minus 4 pi mv over gamma of 1 minus k multiplied by e to the minus 2 pi v. There's probably supposed to be an m there. B. It's not too surprising that the incomplete gamma function would show up here, since it showed up yesterday. Okay? And what this tells us is that delta k of bm of v e of mu is 0, and so we get something that's annihilated by the Laplacian, and so this should be a harmonic Maass form. So for what I'm going to write down here, let's assume that k is less than 1/2. By the way, I don't think I've mentioned this before, but remember there's this duality between k and weight k and weight 2 minus k because of the Cassie operator. The dividing line there is 1, the line of symmetry, and that's why k equals 1 is sort of bad. We don't talk about that too much. It's just wildly different theory than anything else. But there's a couple of other kind of special numbers here. So one is this line of symmetry. 0 and 2, these are sort of the edge. These are the edge of where convergence is nice. Where constructing Poincare series that converge nicely. This is sort of the edge of where you can do things nicely. So in these regions here, it's very easy to construct Poincare series that converge nicely. But my favorite two weights are 1/2 and 3/2. I think these are some of the most interesting examples of modular and Mach modular forms that exist, because these are where the theta functions and the Mach theta functions live. And those are the ones that I think are the most interesting, but they live in this sort of no man's land region of bad convergence. And I'm going to talk about that again later. This is sort of a whole thing to say there. But for this, I'm going to just assume that we're in this nice region over here. 0 ends up being not so bad, so we can assume k is 0 for this. Okay, so let's if we plug in this phi, I'm going to call these FKM. Let's say that's P of phi m tau in this case. If m times n is negative, then what you end up getting is a bunch of I Bessels from the integral. And if m times n is positive, then you end up getting a bunch of J Bessels. And it's actually more striking than that, because if you look at the actual formulas, which I'm not writing down, but if you look at the formulas, they really resemble these in a striking way. And so we're going to see a hint of that in a second. But okay, so if m is negative, then this FKM lives in HK gamma 0 n nu. And remember HK without the exclamation mark. These are the ones whose the shadows are cusp forms. Okay? And if m is positive, then FKM is in HK sharp. And remember, these are the ones for which the shadow is weakly holomorphic. What's that? Oh, this n. So we're looking at the nth coefficient, right? The nth coefficient. The reason I didn't have an n over there, so the nth coefficient, n is going to be positive because these are holomorphic modular forms. There are no negative n terms, except maybe this q to the negative. But n is always positive in this case. But here, these are harmonic Maass forms. So they're going to have the holomorphic part and non-holomorphic part. So they're going to have the negative ends and the positive ends. So this is the Bessel function that you get is determined by the sign of m times n. Okay. So what happens when we start hitting these with the various differential operators that we talked about yesterday? So if you take FKM and hit it with CK, what you're going to get is P 2 minus K minus M. Remember that, well, when M is negative, this thing should have a shadow that's a cusp form. And the shadow is, well, if M is negative, then minus M is positive. So this is a cusp form. Okay, so that makes sense. And in fact, at this point, we can now prove, that the C operator is surjective, because these span the space of cusp forms, and here's a preimage. There you go. Okay. What happens with D? So D 1 minus K, probably K minus 1 if I'm working on FK. K is negative, so I do want D1 minus K. Thank you. So this will give you P2 minus Km. Okay? And the flipping operator, so what is this? I'm just going to call it flip. The flipping operator gives you Fk minus M. And these are only valid in integer weight. So you can see these differential operators really play nicely with all the Poincare series. It's a very nice, neat theory. And actually, if you do look at the formulas for the coefficients very closely, you can see like relations among all of these. And if I had 20 minutes to sit and write formulas down, we could look at it, but I just don't feel like that's worth our time. Are there any questions at this point? What's that? Do they generate? Yeah, so they'll, let's see, is that obvious? Should, yeah, right. Yeah. All right, let's do another example. Let's see. Yeah, so you should be able to use, you use the pairing here as well? The Bruinier and Funke pairing?
Yeah. The order, there is a pole, got a basis for one of those poles.
Right. So each one of these is going to have a really distinct, like a distinct q to the negative m term, the order of the pole in the holomorphic part. And once you know the principal part of a harmonic Maass form with a specified shadow, then you sort of know the whole thing. But because I believe you said that in your talk, right? If you know the principal part
Yeah.
and the shadow, then it's right. Yeah. Yes. At other cusps. Yeah. So you can do this whole calculation looking at other cusps. So whenever there's like a growing term, it doesn't show up at any of the other cusps. So what the general formula, this has a delta mn. There will also be a delta for if the cusp is infinity, and then this term just sort of doesn't show up otherwise. That makes the calculations quite a bit more complicated for other cusps, but it's along the similar lines. Yeah. Okay. Let's see. I end at 12:30. Is that right? Yeah. Okay. Good. Perfect. Actually want to start over here on the left. This example is a longer one. So I said that weight 1/2 and weight 3/2 are the interesting weights, but they're also the most complicated ones. So let's do an example where the weight is 3/2, and we'll see some more examples on future days in weight 1/2. Okay, so this example is Zwegers weight 3/2 Eisenstein series. You'll notice that in none of the special cases I've talked about yet, I haven't mentioned m equals 0 ever, but this will be our first example of an m equals 0 thing. So I'm going to set the weight to be 3/2. I'm going to set m equals 0. I'm going to set phi of v. So really this would be phi 0, but I'm not going to put the 0 in. So phi of v, this is going to be v to the s. And this s is going to be some auxiliary parameter that for now, we're going to take real part of s to be big enough for things to be nice. Let's just make it easy on ourselves and say real s is bigger than 1. I'm not even sure you need that. Let's say that the group is gamma 0, 4. And let's say the multiplier system is the theta multiplier, as usual. Okay. Then the Poincare series that we get, we can write it down maybe even more explicitly. So this will be a sum over all gammas in gamma 0, 4 mod gamma infinity of nu bar of gamma over c tau plus d to the 3/2 times absolute value of c tau plus d to the 2s. That's what you get if you plug all of this stuff. Now, if we want something that's a weight 3/2 modular form, what we really want to do is get rid of this s dependence. And we want to say, we're gonna eventually want to take the limit as s goes to 0. Now, we're not allowed to do that right now because it doesn't converge. So, so for the sake of convergence, we'll leave s, but then in a little bit, we'll set s to be 0. And then we're gonna have to do something that's a little bit frustrating, and I'm not gonna put a lot of detail into this, but it's called projection into Conan's plus space. So we're gonna project into the Conan plus space. The Conan plus space is characterized by having coefficients supported on indices -1 to the k minus a half n is congruent to 0 or 1 mod 4. Why would this be a thing you would think about? Well, in weight 1/2, the theta function the usual theta function is supported on squares, which are all 0 or 1 mod 4. So that might be your first indication that this is something interesting. So this is a special space, a subspace in any half integral weight space. And I'm not going to say too much about it, but what I will say is how you actually do it in this case. So I'm going to have a function called h sub s of tau. And this is just the formula. This is just what it happens to be. 1/96 I e of tau s minus 1 minus I tau to the minus 3/2, absolute value of tau to the minus 2s, e of minus 1/4 tau s. And I just don't think that's enlightening at all, but I mean, there it is. So this is what projection into the plus space looks like for this function. And what this is going to do is you can compute what it does to Fourier expansions, and it's very complicated. Well, it's not hard. It's just very, it's nitpicky. But what it essentially does, the essential effect, at least for Poincare series, the essential effect is that it replaces the Kloosterman sums by different Kloosterman sums that are very closely related. And I'm going to call these S plus M and C. These are the plus space Kloosterman sums. And I won't put the dependence on the multiplier anymore because it's a fixed multiplier system now. And this S plus, this is just 1 minus I times the original Kloosterman sum multiplied by either 1 or 2. And it's 1 if C over 4 is even, and it's 2 if C over 4 is odd. And that's the effect that it has. And it's just this sort of very long calculation that eventually gets down to this very pretty formula. Okay, so what we want to do, we want to study these plus space Kloosterman sums for a little bit, because we're going to compute the Fourier coefficients of Zagier's weight 3/2 Eisenstein series. I'm not going to do every single step, but I want to just give you sort of the flavor of the calculation and how it goes. So now if we look at this formula, this Vm, this is just V to the S. So I'm basically taking this to the S. That's what's happening, right? And let's look at just the C dependence. There's a C squared here. And so I'm going to get a C to the 2S in the denominator. Okay, C to the 2S. And M is 0, so this part goes away. So the only C that shows up is a C to the 2S. So what we're going to get is some kind of Dirichlet series. So let's just call this thing, oh, I used phi already, that's bad. Let's call it, I don't know, something else, psi of NS. Let's let this be the Dirichlet series that we get. So we need 4 dividing C. So remember, there was a C to the 2S. For simplicity, let's just say C to the S, and then at the end, we'll replace S by 2S. So there's a C to the S in the denominator. And there's this S plus, well, remember, M is 0. So this is 0 NC. So there's some kind of Dirichlet series that we form out of the Kloosterman sums. We're going to evaluate this. We're going to actually write down what this is, at least in some special cases, so that you can kind of see how this goes. It is going to be some Gauss sum looking thing. Yeah, that's right. Yes. Mm-hmm. All right. So we're actually going to do this using what's called Conan's identity. And this isn't the only way to do this, but it's a way I like because it generalizes nicely. So Conan's identity is an identity involving these plus space Kloosterman sums in terms of some other sums that are quite interesting. So here I'm going to assume that n is equal to, I'm going to write it as d, that's a fundamental discriminant. A fundamental discriminant, if you don't know what it is, then just replace in your mind the phrase fundamental discriminant by square free. That's sort of close enough. It's either a square free or it's 4 times a square free. Okay, so we're going to assume it's fundamental. Then Conan's identity is more general than this, but it's just a bit more painful to write down, so I'm just gonna write it down in the fundamental case. So instead of M and N, I'm gonna call it D prime and D, and we're only assuming that D is fundamental, D prime can be anything. So it turns out that this is square root of C over 2 times some other sum called T, D prime, D, or C, where T of D prime, D, or C is the sum over all B's mod 4C, such that B squared is congruent to D times D prime mod 4C. And then there's going to be a character, which I'll talk about in a minute. I'm going to put some stuff in there, multiplied by just an exponential factor, E of 2B over C. Okay? And this sum is going to be related to integral binary quadratic forms of discriminant D times D prime. So I'm going to fill that in just a minute. But this chi sub D is going to be a character from the group of integral binary quadratic forms of discriminant D, D prime. And it's going to spit out either 1 or 0 or minus 1. It's going to be some character of this group. And so in here, we're going to have to put an integral binary quadratic form. And I'm going to do that by just specifying the 3 coefficients that it has. And they're going to be C, B, and then once you know the first 2, you have to know the third once you know the discriminant. And so it's just going to be B squared minus D, D prime over 4C, just because that's what it has to be for the discriminant to be what it is. Okay, and I can tell you exactly how chi D is defined. So chi D of a binary quadratic form ABC, well, this is going to be either, it's going to be either the Kronecker symbol D on N, if N is represented by the binary quadratic form. So AX squared plus BXY plus CY squared for some X and Y in Z. And then it's, and I need to know that the GCD of A, B, C, and D is 1, and it's 0 otherwise. And so your first question, I'm sure, is, well, what if I pick a different N than somebody else? Well, it turns out that you'll get the same answer. So it doesn't matter which N you pick any N that's represented by the quadratic form, and you plug it in here. So this is some character. And you get this sum. And I think this is a really beautiful formula, which it may come back in a future lecture, but I think it's really nice. And oftentimes, if you're dealing with half integral weight modular forms, there's a good chance that this identity sort of is sitting in the background somewhere, even if it's not explicitly written down. Okay, well, what are we going to do with this? So let's compute T0, D, or C. So this is the sum of B's mod 4C, such that B squared is congruent to 0 mod 4C. Oh, by the way, I didn't originally have any of this in my notes, but I kind of got this wild hair last night and thought, I want to show this to you. So there's a good chance that I got some of the powers of 2 incorrect. Powers of 2 are notoriously difficult to get correct. And so there's a good chance that I'm off by some power of 2 somewhere. So maybe don't take this to be so gospel truth, but the idea will be correct. So chi D of C, B, B squared over 4C, E of 2B over C. And here's what we're going to do. So we're going to write 4C as T times U, where T is a product over all of the prime divisors of 4C. So P to the A exactly divides 4C. And we're going to take P to the floor of A over 2. And U is just going to be what's left over. So it's a product over the exact same thing. P to the ceiling of A over 2. Okay? Then, and you can check, I'm going to write down some things that I'm not going to fully explain, but these are all like pretty easily checkable. B squared is congruent to 0 mod 4C if and only if B is X times U for some X mod T. And so here's what we'll do. We're going to let G be the GCD of X and T over 2. And you can show, and again, this is a thing you should check. You can show that the binary quadratic form CB B squared over 4C is equivalent to another one that looks very nice. It's equivalent to one that looks like UG squared over T 0, 0. Okay, and that's, you can actually write down an explicit matrix in SL2Z that you can hit this with to get this. Ceiling, yeah. Okay, well now if we're asking the question of what numbers are represented by the quadratic form, well now this quadratic form is quite nice. I know all the numbers represented by this quadratic form. And in particular, I could just take UG squared over T as n. And so T of 0 D4C, well, it turns out that this is 2 pi d of, and we can just put U over T, the G squared of course doesn't matter, sum X mod T over 2 such that X, T over 2, and D are co-prime. And we'll take E of X over T over 2. Okay, I'm doing some simplifications here that I'm not telling you about. So again, these are all things where maybe there's a step or two missing that you can fill in on your own. Okay, so let's evaluate this in some cases. So there's a couple of things to show. The first one to show is that T is multiplicative as a function of C. And that's not too hard to show. You can just sort of explicitly write down a product and work it out. And the second thing is let's actually check what it looks like on prime powers. So if P divides D, and for simplicity, let's say P is odd. This is actually still true if P is 2, but it's maybe a little bit more complicated. Then F of P to the A, wait, did I say F? Did I tell you what F is? So let's call this thing 2F of C. It turns out T is not multiplicative, F is multiplicative. T is 2 times a multiplicative function. Multiplicative functions are usually 1 at 1. That one would not be 1 at 1. Okay, so F of P to the A. So let's think about this. If A is odd, then what happens? Well, if A is odd, then U has a power of P in it, sort of an extra one that T doesn't have. And so U over T will have a factor of P in it, but P divides D. And so chi D of that is going to be 0. So we'll get 0. And if A is even, well, if A is even, then what ends up happening is that this factor turns into a Ramanujan sum, which you can show evaluates to just the Mobius function. So this evaluates to mu of e to the a over 2. And again, that's just a detail that you can check. So that's because this is a Ramanujan sum. If P does not divide D, again, let's assume P is odd, but again, this is still true for P equals 2, then F of P to the A is, well, it's going to be something, well, let's write it like this. It's pi d of P to the 8th power by just sort of plugging in what U over T is, multiplied by, well, if P does not divide D, then this GCD is always 1. And so this condition doesn't exist. And so you have a complete sum of exponentials, which is going to be 0, unless T over 2 is equal to 1. So you'll get 1 if T over 2 equals 1, and it's 0 otherwise. Okay, so we've evaluated t in every case. Well, except when p is 2, but you'll just have to trust me on that one. Okay? All right, so now we can write down this Dirichlet series, and this is where the fun happens, because we're going to actually get something kind of cool looking. Okay, so if we take the sum, c equals 1 to infinity of f of c over c to the s. Okay, well, f is multiplicative, so we can write this like a product over all primes of the sum L equals 0 to infinity of f of p to the L over p to the ls. Okay, well, and we need to split into two cases where p either divides d or it doesn't divide d. If p divides d, that's way over here, I gotta walk so much. Okay, if p divides d, then we're only going to get a non-zero contribution if a is even, but also we're taking the mu function of p to the a over 2, which means if a is any bigger than, if it's 4 or bigger, we're also gonna get 0. So actually there's only one thing here, which is a equals 2, is sort of the only case that matters. And so everything else is 0, and so what we end up with here is 1 plus, well, mu of p is minus. So 1 minus 1 over p to the 2s. Okay? Let's do the same thing for p not dividing d. T over 2 equals 1 is the same thing as saying, well, that means that a had better be 1. And that's the only case in which that happens. So a equals 1, otherwise we get 0. And so we get a product here of 1 plus pi d of p over p to the s. I realized I didn't actually tell you what this chi d means when I don't plug in a quadratic form. This is just the Kronecker symbol, chi d. Okay, so we have an Euler product. Let's turn this into something recognizable. So let's write this like, let's say, product p does not divide d of 1 minus p, 1 over p to the 2s to the minus 1 over product over all primes 1 minus 1 over p to the 2s to the minus 1. Okay, what did I do? I just took this piece and I kicked it in the denominator, and then I put whatever I needed to fill in all the stuff, so I get a Riemann zeta function. Okay, and then here, I'll just write this like 1 over product over all primes of 1 plus chi d of p over p to the s to the minus 1. And now why am I allowed to fill in all the extra primes? Well, for the primes that divide d, chi d of p is 0. So it's actually automatic. And now what we're going to do is we'll take this and let's just factor this. It's a quadratic, right? It's a difference of squares. So we're going to factor as, let's factor it like 1 minus chi d of p over p to the s times 1 plus chi d of p over p to the s, both to the minus 1. And then there's some cancellation, and you can sort of collect everything together. And what you're going to get is a Dirichlet L function, ls chi d, over zeta of 2s. So this Dirichlet series of Kloosterman sums has some really interesting number theory in it. It's got values of Dirichlet L functions just sitting there, which is delightful. So I've just a couple minutes. Let's do just a couple more steps and then we'll be done. So if we go back to this thing which I called psi of ns, right? That was our original Dirichlet series. Well, let's see. There was a square root of c here, which means it shifts the value of s a little bit. And remember, I was going to plug s. I was going to plug in 2s instead of s. So what we end up getting is 1 over square root of 2 L 2s minus a half chi d. over zeta 2s minus a half, zeta 2s, let's see, 4s minus a half. Let's see, did I do that right? Yes, I'm missing one more thing, which I was going to show you when I had that formula up right there, and I forgot. Remember, there was a sum over c's, and there was like a c to the minus k, and then a sum over d's. So we are actually off by, there's an extra c to the minus 3/2. So what we really are doing before we plug in s equals 0, so the coefficients of this weight 3/2 Eisenstein series of Zwegers contain things that look like L2s plus 1 chi d over zeta 4s plus 5/2. We're off by 3/2. And now we're evaluating at s equals 0. Because remember, I said that that's what we wanted to do at the end. We're evaluating at s equals 0. Well, in the denominator, we're just going to get some constant. But in the numerator, we're going to get something really interesting, which is L1 chi d. Okay? And now we can use the class number formula to say, well, this is going to be a regulator times a class number. We've seen these before a couple of times, I think. Certainly yesterday we saw the class numbers, h of d. Something else is going to happen. Remember I said d has to be a fundamental discriminant, so otherwise we would have a formula that involves like a square factor times a fundamental discriminant. And so if our number was a perfect square, then our fundamental discriminant would be 1. And L1 chi 1, well, that's just the Riemann zeta function at 1, which is actually a pole, okay? And you can show that the special function that you get in that case actually has a 0, and they cancel out. The pole and the 0 cancel out. It's actually kind of a fun little calculation, which I just don't have time to do. And so let me write down the final theorem for you, and then that will be the last thing, and we'll be done. We'll go to lunch. So here's the theorem of Zwegers, who did not prove this the same way that I just did. Okay, so let h of n denote the Hurwitz class number function. When n is a fundamental, or when negative n is a fundamental discriminant, this is just the usual class number. Otherwise, it's a sort of weighted sum. Let's let script h of tau be the function minus 1/12 plus the sum n equals 1 to infinity, h of n u to the n, plus 1 over 4 root pi sum n equals 1 to infinity, n gamma of minus a half 4 pi n squared v q to the minus n squared. And then there's plus 1 over 8 pi root v. Okay, we sort of computed, I didn't do all the special function stuff, but we sort of computed these. And then I hinted at, well, when n is a perfect square, something interesting happens, and that's sort of what happens over here. There's a pole and a 0 that cancel out, and so we end up with some sort of leftover stuff here. But then the theorem is that this h is in h3/2 shriek gamma 0, 4. And let's put a little plus here because it's in the plus space. So this is a weight 3/2 harmonic Maass form whose coefficients encode class numbers of imaginary quadratic fields. Furthermore, also, the C operator applied to H gives you exactly the usual theta function supported on squares, which is weight 1/2. So, and this is probably the first interesting example where we really sort of understood what was going on of a half integral weight harmonic Maass form. Certainly there are other examples in the Mach theta functions, but it took longer to understand what was happening there. This was like a sort of early example of that. Okay, that's a good place to stop, so I'm done.
Okay, thanks a lot, Nick.